Hi everyone, this is section 6.3 on vectors in the plane in R2. In your Math 252 class, you'll talk about vectors in 3-space, R3. So first of all, before we talk about vectors, we need to talk about scalars. A scalar has magnitude, but not direction. So can a scalar be negative? It depends on the context. For example, later on, when we think of real numbers as scalars, then scalars can be negative. That's okay. An example of a scalar is a speed, such as 55 miles per hour. That's a scalar quantity. It has magnitude, but not direction. And again, sometimes scalars can be negative, although here speed cannot be. But then we have vectors. Vectors have both magnitude and direction. Magnitude and direction. There's a clip from Despicable Me I can send out. There's actually a character called Vector. Now, a vector can be written in various ways. So, for example, it might be written with a half arrow on top. Like when I'm writing symbols for vectors, if I'm writing on a whiteboard, I might write it with a half arrow on top. Some books would put like a ray notation, a half line on top. In my notes, I denote vectors using boldface. That's fine for my notes for typed print, but of course, it's hard to write boldface when you're writing with a pencil or a pen. So if you're writing with a pencil or a pen, I might recommend this sort of half arrowhead version over here. That's what I would tend to write on a whiteboard. But you need to indicate the distinction between a vector and a scalar. You absolutely have to know a difference, because on homework and on exams, I often have questions, and these are hard questions, right? For university students, these are hard questions. Here's an expression with scalars and vectors in it. Does this expression represent a scalar, a vector, or is it undefined? And those are really hard questions for university students. They're some of the hardest. So know it's a scalar, know it's a vector. And write these down accordingly. Now again, a vector has magnitude and direction. The magnitude is denoted by this here, which is this boldface V, or the half arrowhead on the V, with a pair of vertical bars. Actually, 2 pairs. Actually, it's 2 pairs of vertical bars around the V. This is sometimes called a norm or length or magnitude. So again, this is often referred to as not just magnitude, but norm or length. It's a numerical measure of the vector. It's typically associated with its length. The length of a vector indicates its magnitude. For example, the directed line segment, this arrow guy below, is a velocity vector. This here is a velocity vector, which again we can denote with V with a half arrowhead on top. This is a velocity vector, which has magnitude. That's the length of the vector, which is in fact the speed. The magnitude of velocity is the speed. And the direction here is, of course, the direction in which the object, such as the car, is going in. So here, the car, let's say, is going in a somewhat northeasterly direction. A vector has magnitude, like speed, and direction. The magnitude, the speed here, is the length of the vector. This vector is equal to this vector. So these are 2 representations of the same vector. These are equal vectors because they have the same magnitude and direction, even though they don't hold the same position on the page. So remember, vectors are characterized by magnitude and direction, not by position. We have the right to move these things around. These are 2 perfectly good representations of the vector V. They have the same length and the same direction, but not necessarily the same position. These are equal. Now, the direction of the arrowhead does matter, okay? So here, this vector is going from this initial point to this terminal point, We can think of this as a displacement vector. It's like we're walking from this point to this point. It turns out that the opposite of v will take us from this point over to this point. This would be the initial point here, and this would be the terminal point here. These are not equal vectors. In fact, these are opposite vectors. These are opposite vectors. So it's not like a line segment where I can ask you, what's the slope of this line segment? It doesn't matter which order we take the points in if we're doing slopes. But here, it matters what direction the vector is going in. These two vectors are opposites. They have the same magnitude, but they have opposite directions. So what about the geometry of vectors? How do various operations on vectors affect their geometry? Let's talk about scalar multiples of v, which is given by, and this is what I mean when I say that it's important to know the difference between a scalar and a vector. What's a scalar multiple of a vector? A scalar multiple of a vector could be something like 2v, 3v, negative 1v, or the opposite of v. Okay. But remember, we need to indicate clearly what a vector is. So if I can boldface these, right? Whoops. So So if I boldface the v, whoops, can I just boldface one? Right. So the idea is that I try to boldface the v. I don't know if I can do just him. All right, but I'm supposed to boldface the v. I guess I have to do this. So here's 2. Here's v. And I'm going to boldface the v. There you go. So here we have a scalar multiple of a vector, like 2 times v, 3 times v, and so forth. All right, so CV, where C is some real scalar, like 2, for example. In this case here, C could be negative, like negative 2 or negative 1. Okay, so the new vector, CV, okay, this is a scalar C times a vector V. The V here is bold-faced. Although if you're writing this, then you might want to write the V with a half arrowhead on top. You have to indicate a vector somehow. Now, the length of this new vector will be the absolute value of C times as long as V. So for example, 2V will be twice as long as V, but also negative 2V will also be twice as long as V. So both these vectors, 2V and negative 2V, these will be twice as long as the original vector V, as vector V. All right, I guess I'll put the half arrow on here. All right, and if C is negative, then CV points in the opposite direction from the direction V points in. So if this is the vector V, all right, again, 2V, same direction but twice as long, but the opposite of V would go like this. Same length, but opposite direction. Negative 1/2 V would point in the direction of this guy, but will be half as long. The absolute value of the scalar multiplier gives you the multiplier on the length. That's why I say the absolute value of C. That's the multiplier on the length. Bear in mind, there's also 0V. 0V is the zero vector, which is denoted by or indicated by a point with no arrowhead. But the zero vector is a vector. All right. How do we add and subtract vectors? Vector addition can correspond to combined or net effects. So for example, if V and W are force vectors, then the resultant vector, the sum here is called a resultant vector, V plus W, this would represent net force, as we'll see. Vector subtraction may be defined as you might suspect. So to subtract a vector, you're adding its opposite. That makes sense. That's what we do with real numbers. You add the opposite. So what are a couple of ways that we can graphically represent vector addition? One is the triangle law. And this is especially helpful for ideas of displacement. So let's say that you're here at a palm tree, and if and when we're allowed to go outside, right? So we're at this palm tree here, all right? We dig underground and we find a treasure map. The treasure map says, okay, to get to these concert tickets over here, when we can get concerts. So think of your favorite band, okay? And your favorite band's concert tickets are at this spot here. The treasure map tells you that you have to start at this palm tree, follow the displacement vector v over to this point, and then follow the displacement vector w to get to this point, and then you dig and get your favorite band's tickets. So here, what's the resultant vector? Well, you may as well, as the net result of all this, you may as well have started here at the palm tree and gone straight to the point with the tickets. So this would be the resultant vector v plus w. It's easy to see as a sum of displacement vectors. You ultimately started at this point and you ultimately ended at this point. So the head of this arrow is attached to the tail of this arrow. It's like you're following these steps. Again, better for sequential effects and displacements, like walking. But what about that force example I gave before? So imagine that there's a pool table with a pool ball, like the white cue ball, for example. Right. I remember watching an episode of 1,000 Ways to Die. There is this foolish person who liked to sort of kind of swallow, kind of half swallow pool balls. And he died when he swallowed, guess what? The biggest ball, the white cue ball. So don't swallow cue balls. All right, anyway, that's your lesson for today. Okay, so speaking of pool, all right, imagine a pool ball here, right? And imagine a pool table that is frictionless. That's not realistic. You almost have to think of an air hockey table almost, but imagine a frictionless pool table. We have a pool ball here. Imagine that one cue stick, like one wooden stick, hits the ball in this direction, and the force applied corresponds to the length of this force vector. And another cue stick, a second cue stick, hits the ball in this direction, but with a greater force, corresponding to the length of this force vector. So the idea is that when you combine the effects of these two forces, you may as well have hit the ball with this net force, this resultant force vector. This is the resultant force applied to the ball in terms of direction and the net force, the magnitude of the net force. It's called the parallelogram law because you can draw this resultant vector by setting up these two vectors so their initial point is at the same point, right? The point where you hit the ball. And then you form the parallelogram formed by this point and these two vectors as adjacent vectors, as adjacent sides on the parallelogram. Then you fill out the parallelogram, draw this diagonal from this point here to this kitty corner point over here. That's the parallelogram law. The triangle law, you can see why it's called the triangle law, right? You're completing the triangle. So that's how you add vectors. And again, to subtract vectors, you would add the opposite. So for v minus w, okay, you would take the v vector over here, and you would add the opposite of w. Okay, and that resultant vector would look more like this when applying the parallelogram law. All right, v plus wb here. Again, better for simultaneous effects and net force, as opposed to sequential effects and displacements. Next up, we're actually going to play with coordinates. We're going to put these vectors in the rectangular or Cartesian plane next time.